Welcome back, everyone. So I want us to go through our SafeBite project. My name is Wilson, together with Musinguzi Mark and Rubanken Emmanuel Brady, and our group. This is group SWAI 34. And before we begin, our main target customers are local food vendors and chapati stores, customers seeking for safe food environments, were Kampala Capital City Authorities, and National Environment Management. And this is a simple demonstration of
So
how
now this is
of
an
our
interface
AI
for the
system works. And
customer. As
this is a
you can
front
see,
end
they're provided
mainly,
with the
so the
satisfied
customer's view on a mobile
authentically the
application,
records that they
a
want.
laptop, or any
So
other
as right now,
device. And it also
there are
shows
no
the
locations loaded.
our
Let's
client's
wait
view, for
as
example,
the
the
locations
store
first load.
owners and the chapati store owners and the local restaurant owners, the
So
dashboard
now
they're in,
as
where they can view the
some
air
sample
quality,
locations have
the
been
rewards,
loaded.
badges, and
As
their
you can see, we
visibility
have a
boosts.
short, we
Uh,
have very few samples. We
and
have
our
6 of
system
them,
right
but
now is currently
so
deployed.
now
And so let's go through the problem space and the purpose. So our main objective is to design and deploy an AI-driven low-cost air quality monitoring and incentive system that uses spatio-temporal modeling and intelligent recommendations to detect, predict, and reduce harmful air pollution exposure in Uganda's informal spaces. And our core problem is that air pollution in informal food spaces such as roadside eateries and chapati stores exposes customers and vendors to high levels of smoke, carbon monoxide, nitrogen dioxide, and fine particulate matters, PM2.5. And who experiences it most? Well, mainly food vendors working long hours in poorly ventilated environments. These are chapati stores mainly, and customers who spend 2 to 30 minutes per day visiting in high smoke areas. University students, and then urban residents and municipal health departments lacking localized exposure data. Then we can also look on how AI is essential in this problem space. How can it help us solve this problem? And we can say that AI enables spatial temporal reasoning over complex, noisy, and irregular sensor data. Something manual methods as or simple automations cannot do. Remember, our data is going to be captured in a raw format, so we can use AI, the artificial intelligence, to enable the reasoning over this very irregular data. And below are the measure impacts, the social, behavioral, economical, and technological impacts of our AI system. So below our users, stakeholders, and ecosystem actors in a system. So the primary users are food store vendors and small restaurant owners. Those are the ones that have the first hand in the system. And then the secondary stakeholders are the KCCA organization, NEMA organization, Ministry of Health, and NGOs. And the ecosystem roles. We have sensor manufacturers, data analysts, and back-end AI developers. And then governance entities that take part in this system is Makerere University, AI Ethics Board, and then the Uganda Data Protection Office. So about the data sources and values, our objective is to build a spatial-temporal data set of air quality in informal food spaces using low-cost, multi-pollutant input-output sensors, sensor nodes enabling data-driven public health interventions, behavior recommendations, and also incentive-based decision-making systems. And our system was trained using datasets from Aircore and very many other sources, but so the system uses data that was collected from low-cost IoT air quality sensor nodes deployed in informal eateries across Kampala, supported by Aircore, open data, and on-site calibration logs. So additional metadata such as timestamps and GPS coordinates were embedded during transmission. So let's talk about the solution and the AI system description. And the objective is to design an AI-driven spatial-temporal monitoring and recommendation system that analyzes real-time air pollution data and provides context-aware actions and incentives to reduce exposure in informal food spaces. Mm. And there was a couple of AI methods and algorithms used in our system, and some mentioning some temporal reasoning. We used LSTM and transformer-based models for time series forecasting. And then for spatial reasoning, we used the graph attention network (GAT) for site-to-site pollution propagation. Then our decision intelligence, we use a neurocontextual policy, which is reinforcement learning for behavior recommendations, and for explainability, we use the sharp-based feature attribution for transparency and trust. And then briefly about model inputs and outputs. Model inputs are basically the pollutants, PM2.5, carbon dioxide, carbon monoxide, temperature, humidity, so any other pollutant, and timestamps and even the location. So the output is a predicted ETSAFE score or SafeBite score, and the recommended mitigation action like open window, reduce top load, and any other alerts. So about key metrics and evaluation, our objective was to evaluate the performance and fairness and the impact of the AI-driven SafeBite system across technical, user, ethical, and business dimensions. And a little bit of the metrics. Our mean absolute error was roughly 2.6. Then our root mean square error was 4.9. And then our our system uptime was greater than 98% during deployment. And the rest of the metrics have been listed as shown above. And then for unfair advantage and differentiation, so objective was to highlight the unique strengths and defensible advantages of the SafeBite AI system that makes it difficult to replicate and sustainable in the long run. So our key differentiators are so first of all, first-time real-time air quality data from Uganda's informal food spaces using custom low-cost IoT sensors, and then hybrid AI framework. This is so because it combines temporal transformers, graph neural networks, and context-aware policies for robust spatial temporal modeling, and then also behavior-linked incentives, which are directly ties AI recommendations to actionable improvements, motivating clean air practices. And then also resource constrained optimization, which is through offline fast, low power design tailored sensors, which are able to work even in offline areas. And then for the channels and distribution, the objective was to show how users discover, access, and engage with a SafeBite AI in informal food spaces. We can use acquisition channels, which are on-site awareness campaigns as local eateries and markets, social media outreach via WhatsApp or Facebook, and then local forums, and then partnerships with our NGOs, municipal health authorities, and universities. There's also through use of mobile applications and SMS stroke USSD for low-tech accessibility, web dashboards for municipal authorities and health inspectors, and even APIs for third-party platforms integration. And then for our revenue streams, the objective is to outline how the SafeBite AI generates income and sustains operations. Well, one is through direct revenue models, which are subscriptions for dashboard access and reporting license fees for municipal and NGO deployments. It's a pay-per-use APIs for third-party platform integration. And then we can also offer free basic features for small eateries and paid premium analytics or custom deployments for larger organizations, which is a freemium and tiered access. And also through value-added streams, which is sponsored research and pilots. Then about the key resources, one is the human resources, which are the AI engineers, data scientists, are developing the LSTMs, the DATs, and policy models. We also have the UX designers refining the itself score dashboards and mobile interface. Then the environmental scientists, public health experts, and ethicists ensuring responsible and context-aware AI development. We also have the technical infrastructure, data infrastructure, and financial resources. So going through the key activities, one which is the model lifecycle activities. This is collecting, calibrating real-time sensor data from informal food space eateries, and then train and update spatio-temporal models to predict air quality and SafeBite scores. Then also validate and deploy recommendations via mobiles, SMS, USSD, and dashboards. And then product development activities, which is design user-friendly dashboards and mobile interfaces for vendors and authorities. Also develop APIs for integration with municipal systems and platforms, and also feature engineering for multi-pollutant data and behavior-linked incentives. And then also there was the optional activities, which is tracking sensor network performances, data quality and system uptime, and also governance and compliance. And the last was a customer-focused activities, which is providing technical support and training for vendors. So the key partners, the objective is to highlight partnerships that amplify product reach, data access and governance, and scaling capacity. And then technology partners, we have local IoT hardware vendors for low cost deployable sensor nodes, sorry. And then cloud providers like AWS, GCP for scalable storage and analytics. And then AI research labs for advanced spatio-temporal modeling. And then we also have data partners, which is for universities like Makerere University for research, support, and calibration. Then ethical oversight partners, we have collaborated with the National Council for Science and Technology and the Uganda National Bureau of Standards for responsible deployment. And then distribution partners are telecommunication companies for SMS, USSD delivery to vendors. And then strategic collaborators, was the last one. And our cost structure was as follows. Data costs, this included sensor deployment, calibration, and maintenance in informal spaces. Also data cleaning, interpolation, anomaly detection and storage, and licensing fees for complementary datasets like cool. And then also computing and infrastructure costs like cloud storage and compute for real-time processing. There was some costs and also API hosting and bandwidth for mobile, SMS, stroke USSD, and also dashboard services. And human resource costs like salaries for AI engineers, data scientists, ML researchers, UX designers, and product managers. There was also compliance and legal costs, marketing and distribution costs, and maintenance and scaling costs. And then going through the governance, ethics, and compliance. First of all, the governance model, which is we went through an oversight by a dedicated ethics and AI advisory board, including data scientists, public health experts, and local policymakers. Also, for fairness and bias auditing, there was a use of Fairlearn and IA4360 to detect and mitigate biases across location, vendor type, and socioeconomic factors. And then going through scalability and sustainability, there's a scalability framework, which are modular pipelines and microservices for easy expansion to new cities or regions. Containerization with Docker for consistent deployment across devices and servers. And also continuous learning, which is through automatic model training from live sensor data and vendor feedback. So MLOps pipelines ensure adaptive and accurate SafeBite score over time. And we are also looking at localization, which is tailoring alerts, SMS, USSD messages, and dashboards to local languages, cultural practices, and vendor contexts. And then some environmental responsibilities like using energy efficient models and nodes, and also resilience for backup sensor networks, cloud redundancy, and fraud tolerant systems. So going through the intellectual property and innovation, one of the core intellectual assets. One of them is proprietary AI models. Second is the adaptive data pipelines, which are smart processing and anomaly detection methods optimized for low connectivity environments and low-cost sensors. And then also behavior insight engines, AI-driven analysis of vendor compliance and consumer trust patterns over time. And then lastly is a human AI governance framework. And then secondly are the potential protection pathways, which is one is patentable elements through sensor-based contamination detection workflow and hybrid food safety scoring systems. And then lastly are the copyrightable elements and trademark candidates, which talks about the SafeBite Ai name and logo for brand and service recognitions of our system. So through our team contributions, this is a table summarizing our team contributions. Musinguzi Mark, Kaiser Wilson, and Rubankena Emmanuel Brady. And Musinguzi Mark worked with system design, development, and AI integration, which is the technical implementation of our system. And then for research, I myself went to did the research part, data preparation, and model evaluation. So that is a data and analysis area. And then Brady worked on documentation, presentation design, and stakeholder communication, which is a coordination and a communication area design.